All right, so in this video, we're going to talk about something called the VSEPR theory or the valence shell electron pair repulsion theory. And this is what we're going to discuss a little bit more in depth, or more specifically, kind of see in action in lab on Monday in the molecular models lab. And so, what this theory suggests is that electron groups, and when I say electron groups, what I mean are electron groups. What I mean when I say electron groups is lone pairs, so the electrons that are in lone pairs owned by one electron, by one atom, and bonding electrons, or electrons in bonds. These electron groups repel each other through Coulombic forces. Meaning that, these are similarly charged molecules, electrons being negative, and they repel each other just like you would with magnets, through Coulombic forces. And so, like I said, electron groups are lone pairs, single bonds, multiple bonds, and single electrons. And so it's important to make the distinction here that I'll make right now, that when we have multiple bonding, we'll count that whole multiple bond as one electron group. So a double bond counts as one electron group. A triple bond counts as one electron group. And so what this theory focuses on is the repulsion between electron groups associated with specifically the central atom. And when we look at the repulsion of the groups around the central atom, this determines the geometry or the shape of the molecule. And I give you a little photo below that shows, like, here we have our central atom, and these electrons are, this electron right here is pushing against this electron right here. They push away from each other, and through this repulsion, you establish the optimal distance of separation that makes everything happy. So shape maximizes, let me rewrite maximizes separation of electron groups. And this minimizes energy. And so when we do this, like I said, so the shape geometry of the compound with the one central group is determined by specifically the number of electron groups around that central atom, and then secondly, and we'll see this in a little bit, how many of the groups are bonding and how many of the groups are lone pairs. Okay. So we're going to make a distinction between bonding groups and lone pairs. And so we're going to basically shuffle through each of the different types of geometries. And so we're going to first look at compounds with two electron groups around that central atom, and we're going to say that they adopt a linear geometry. And so we're going to start by just looking at cases where we have compounds that only have bonding electrons for our central atom. And the separation of these electron groups is going to be a 180-degree separation. And that maximizes the distance between each of the different components. So this is the maximum separation. And so we're going to look at two cases of this. One is beryllium chloride, which, similar to boron, beryllium actually is happy with fewer than 8 electrons. Beryllium is happy with 4 electrons. And so if we look at beryllium chloride, it has, we can also draw it like this. It has 2 bonds it's forming. This one right here and this one right here. It doesn't have any lone pairs, so we'd say that this has 2 bonding groups. So 2 types of some location of electrons, and those 2 bonding groups are specifically 2 single bonds. And so the way that beryllium chloride looks like is we have beryllium in the center, we have 2 chlorines flanking it, and those 2 chlorines are separated by 180 degrees. A second example we're going to look at is CO2. This CO2, carbon doesn't have any lone pairs, so it doesn't have any electron groups from that. But its 2 electron groups are 2 sets of double bonds. So I've circled those 2 sets of double bonds here. This is 1 and 2. So it has 2 bonding groups, and those bonding groups are specifically 2 double bonds. And just like beryllium chloride, CO2 also adopts this linear geometry. So this loops back to that fact that we have the electron groups for multiple bonds. We count each multiple bond as a single electron group. So multiple bonds, like the double, count as one electron group. Okay? They repel each other very similarly to the single bonding. And so that is our linear geometries when we have 2 electron groups. And right now we're kind of restricting ourselves also to 2 bonding groups. Next, we're going to look at compounds with 3 electron groups, and we say that these adopt a trigonal planar geometry. And in this trigonal planar geometry, we have a separation between the electron groups of 120 degrees. And this also maximizes the separation between our different elements. So 2 examples of this are BF3. So we have BF3, which we can also represent with just our just our lines. This boron has 3 bonding groups, and all 3 of those bonding groups are single bonds. So 3 single bonds. And then we have something like formaldehyde to the left, this CH2O. And we've drawn the correct Lewis structure here. And we have, 3 bonding groups, 1, 2, and 3. So we have 3 bonding groups. And those 3 bonding groups are 2 single bonds and 1 double bond. And so when I talked about CO2, we had that similar repulsion because we had equivalent types of bonds. But when we look at CH2O, our formaldehyde here, because of the double bond having more electron density, because it has 4 total electrons here, it does a little bit more repulsion of the hydrogens, which only have 1 electron group. So we say that the double bond, because of higher electron density, so just more electrons being in that area, because higher electron density has more repulsion. And so we see that the degree of separation between the oxygen and the hydrogens is about 2 degrees larger because it pushes a little bit more, and the separation between each of the hydrogens deviates from that perfect 120 degrees to 116 because they get pushed a little bit more. And so you can think of this in another way, is just that the oxygen is a slightly larger balloon or a larger magnet that is pushing things away from it because it's just a little bit stronger, so it has a little bit more push that gives the maximum separation of the electron groups, just because there's more density up nearby the oxygen. And so these are things that have 3 electron groups. Next, we're going to go to compounds with 4 electron groups, and they adopt something called a tetrahedral geometry. And in this case, up to this point, our linear and trigonal planar geometries have been in 2D space. Now we're in 3D space. And when we look at these tetrahedral compounds, the separation of their electron groups is 109.5 degrees. And so a great example of this is methane. And so I show methane right here. To the right of that, I show a tetrahedron, which is just a trigonal pyramid, where we have our central atom right here, and it reaches out to each of those points. And so I'm showing you that 109.5 degree separation, 109.5. And so when we depict 3D structures, we're going to depict them in a specific way. So I showed methane in this flat form, but it is a 3D molecule. And so to show any of the bonds, like let me highlight it for you. This carbon-hydrogen bond in yellow that's kind of coming at us, and we'll talk about this a lot more on Monday. To depict that group coming out at us, we use a wedge, which is this kind of colored triangle that I'm showing below. This is how we show a bond coming out at us. And then the bonds that are going into and away into the what we call into the board or away from us, like the blue highlighted bond, we depict those using dashes. And so the most correct way to draw methane, showing that 3D geometry, is by drawing this carbon right here in the plane of the board here. It has a planar carbon-hydrogen bond to the hydrogen on top and the hydrogen to the right. And then the hydrogen coming out at us, we use a wedge. And then the hydrogen going away from us, we use a dash. But that's just another way to represent these tetrahedral molecules that have 4 electron groups around them. Next, we're going to look at those compounds with 5 electron groups around them, and they adopt a trigonal bipyramidal geometry, just meaning that you have a triangle base and then a pyramid by having a point above and below that. And the separation of each of these groups differs between what we're looking at. If we're looking at those groups that are in the triangle, so the triangle being, I'm going to highlight it in yellow here, this right here, this triangle, the separation of those is 120 degrees. And so we'll say 120 degree separation of electron groups in the triangle. And a more succinct way to describe these electron groups in the triangle, we'll call these the equatorial groups, kind of like the equator. So equatorial groups. And so equatorial is EQU, ATORIAL, equatorial. And so the separation of our groups that are kind of up and down and those that are in the triangle are 90 degrees. So that's going to be separation between equatorial, so our triangle groups, and groups outside the plane of the triangle. And we'll call those groups that are outside of the plane of the triangle, we'll call these the axial groups. And so when we're drawing this, I had the drawing below to kind of demonstrate what I was talking about with those separations. We put 3 groups in the same plane in a triangle, and then we put 1 group on top and 1 on bottom. And so I'm showing that below here. And technically, the most correct way to depict this is if I look at this geometry right here, we can see that we have phosphorus and then a chlorine, and a chlorine, all of them in the plane of the board because they're not coming out or going away from us. Then we have one chlorine coming out at us, and then one chlorine going away from us. And so we show what a trigonal bipyramid looks like. You imagine you have your central atom right here, and it forms a bond to each vertex here. And then finally, we have those molecules that are surrounded by 6 electron groups, and they adopt something called an octahedral geometry. And so the separation of the electron groups here is going to be 90 degrees because we have 90 degrees between those groups that are in the square, and then 90 degrees between our top and our up and down groups, and then those groups that are in the square as well. And so the way that we draw this is we drew 4 atoms in the same plane in a square, and then we put one atom on top and on bottom. And so the whole reason that we're, doing all these different shapes is that each of them maximizes the separation between each of the given groups. And so we'll look at on Monday the separation. I'll also, for my lab, I'm going to bring a set of balloons, and you'll see that when we grab, 2, 3, 4, 5, 6 balloons, my hand, grabbing the base of the balloon is the central atom. The way that they separate is in these shapes that maximize separation. And so, I'm showing each of these different ways to represent these octahedral molecules. Another way to look at it, using that correct geometry or the correct 3D geometry is we have planar fluorine and fluorine, as we see on our structure on the far right. Then we have 2 groups that are going into and out of the board, and just like this. So this one and this one are this one and this one, and then we have the groups coming out of this as well. And so technically, you could turn it such that it actually looks like this, where you have 4 groups directly in the plane of the board, and then you have only one group coming directly out at your face instead of like slightly out, and then one group that sticks all the way in. So these are 2 equivalent ways to throw the 3D structure. And so this is what the different shapes look like when you only have bonding groups acting as our different electron groups using this valence shell electron pair repulsion theory. When we switch out one of these bonding groups for a lone pair, we'll see that changes the geometry that we observe.